is 4.4, optimization. So I used to think that related rates were the hardest, but I think students in the last few years have claimed that optimization is harder than related rates. So I think a key to remember is that any optimization problem is always an absolute max or absolute min problem, always. So these are always absolute max or min problems. So even if it does not say you must justify your answer, you must justify your answer. So you have to say, why is that the absolute maximum, whatever they're being asked? Or why is that the absolute minimum? Which generally, but not 100%, if we have a closed interval domain, then it's going to be a candidate test, where you're going to take the derivative, find the critical points that are on the domain, plug in the endpoints and the critical points, and pick out the largest one. By doing that, that is your justification. You have shown that the only places where you could have an absolute max or absolute min are in those, and that is the largest value. It's always an absolute max or min, so you're always looking for a value of the function, y value. Where it gets really tricky is when you do not have a closed interval domain, and then it takes a more sophisticated argument. And so sometimes we can be fortunate, and if there's only one critical point on the domain, so if there's only one critical point, there's our one and only critical point, and we're looking at that derivative, then if it, does something like positive negative, then this function must be increasing everywhere to the left, decreasing everywhere to the right. That's going to make that be the absolute max. But you have to say that because you can't do the candidate test because it's not a closed interval. Similarly, if it went negative positive, we could argue that it was decreasing everywhere to the left and increasing everywhere to the right. Therefore, that is the smallest, the absolute min. Now, if it's not the only critical point, then the argument gets tougher. One option is to, instead of plugging in the endpoints, take the limit as it approaches those endpoints. So that might be, if this was 5 and that was infinity, then you might have to take the limit as x approaches 5, not of the derivative, but of the original function, and the limit as x goes to negative infinity of the original function. Now you're hoping that these don't turn out to be the maximum or the minimum, because as a limit, that would mean there isn't a maximum or a minimum. Because it's approaching there, and there's no guarantee that it is actually equal to that value. So we'll see. I think we got an example or two that will bring that up. So a big part of this, though, is just reading through and understanding the problem. Understanding what information is given, what is it that you're looking for. Trying to come up with, you have to get to where you have a function that you're trying to maximize or minimize. So somehow, whether it's an area or a volume or a distance or whatever it may be, you need a function of one variable that you're going to try to maximize and minimize. And then you got to answer that question in the end. So let's start with maybe a not terribly difficult, I hope. Find two numbers. I shouldn't say that. Find two numbers whose sum is 20 and whose product is as large as possible. Whose product is as large as possible. I'm open to suggestion. So if one number is x, what's the other number? Y. So then x plus y must be 20, right? So if one number is x, what's the y equal to? 20 minus x. Okay? And this is, now we want to maximize their product. So we can get a product function. So our product, p of x, what do we mean by product? Multiplier. Yeah. So x times 20 minus x. Well, it's 20x minus x squared. And we're trying to maximize it. So now what do we do?
Take the derivative.
Take the derivative. Let's calculate. So that's going to be, and what are we going to do with that derivative?
That equals 0.
And now, here's where it gets tricky. We got to think about our domain. Do we have any restrictions? I mean, can we say, oh, we only have to look at these values of x, or are we stuck with all real numbers?
X plus 20 minus x has to equal 20. Yeah, that's really well, you could have like negative 21. So it looks
Yeah,
like they're stuck
we
with-
can't say even they have to all be positive, really, right? Because we could get, you know, a negative number and a positive number to be 20. Probably that's not going to give us the largest product because it's going to give us a negative. But I don't think we can actually rule it out of hand. So now this is tough because now our domain is, it's an open interval, right? All real numbers is an open interval. So we can do this modified candidate test. We can evaluate the area at our one critical point. This is one option. We'll do a couple. So one option is we could plug in 10 into our product function. So 10 times 20 minus 10 is 100. And we could take the limit as x goes to positive infinity of that area function. It might be easier to look at it where we've distributed it right here. So as x approaches positive infinity, the behavior is going to be determined by the highest power of x. And so that's going to go to negative infinity. And so that's not going to be bigger than 100. And similarly, we could take the limit as x goes to negative infinity of our area function. And that's going to give us that same result. So now we have justified it because we have done kind of our modified candidate test. So the largest area is going to be 100. Now, because we only had one critical point, we have another option. We could have done our number line for the derivative and say to the left of 10, if we put in, say, 0 into our derivative, then we would get positive or negative into the derivative. So we put in 0, that's going to be a positive 20. If we put in something bigger, like say 20, then we're going to get a negative. So now we could make the argument that this, because the derivative changes from positive to negative, this is a relative maximum. But here's the argument that because it's the only critical point on the domain, then that relative maximum is actually an absolute maximum. And that's a lot to say. So since a prime changes from positive to negative since 10 is the only critical point, A has an absolute max at x equals 10. A lot to say.
So, when we're asked that on the test, you want us to write all of that as like a general rule?
Well, you got a choice.
Right.
So on this particular one, because there was only one critical point, we could have made this argument. If there were multiple critical points, we'd have to plug in the interior critical points, but we'd still have to take the limit as we approach whatever the boundaries of our domain were.
So if you did it multiple, could you still do the number line one and then plug values into the original function and then find which one's highest?
So now, if there's multiple ones, this argument isn't going to work. Because if you think about it, suppose, now this one didn't, but suppose, it changed sign somewhere else. So now it's going to be decreasing, it's going to be decreasing, increasing, decreasing. Now there's no guarantee that this relative max is really the largest value. So that argument isn't going to hold water anymore.
Decimal for relative. Okay.
Yeah. So then you're going to have to hope that wherever our domain is, maybe this does, something like that. And so the limit as we approach that left boundary of our domain is not going to be as big as this. And so then we can say it does have an absolute maximum. But it gets a little trickier. So you can't use that argument unless there's only one critical point. Okay? This will work on any situation. Okay?
Do we have to write any words with that, or do we just show this?
I think we're okay just with this because this is kind of a modified version of the candidate test, a generalization of the candidate test. Okay, so let's do our classic open top box problem. So an open top box is made by cutting squares from the corners of a rectangular piece of tin what did I say? 20 inches by 25 inches. And holding up. How large should the squares be to maximize the volume? I'll do it at the board. Feel like you know what you're doing?
I'm doing my notes, so I have it.
Okay, it's up to you. Here's our visual. 20 inches by 25 inches. Cut squares that are x by x out of the corners. Then you're going to bend those up. And what you're going to get is a box that has no top.
X can only go to 10.
Okay?
Yeah, so do we just like use the value equation and then just like distribute those?
Mm-hmm. But we need where's our x going to come from here? So,
Oh, it's, the thing is just
so this dimension is going to be
25 minus 2x.
and this one's going to be, and then this is going to be, and I think it's probably going to be calculator active, because in general, what you're going to get for a derivative is not going to be something that factors nicely. Now here, it's worth trying to restrict your domain so you don't have to go chasing after critical points that aren't going to give us a positive volume anyway. So the domain consideration, if we want to talk about that a little bit. The domain consideration is, here's our dimensions, our length, width, and height. Each of these has to be greater than 0. So that means that x must be greater than 0, that 20 minus 2x must be greater than 0, that 25 minus 2x has to be greater than 0. That seem reasonable? So if we solve each of these for x here, the first one is going to get us that,
What x is less than or equal to 10?
yeah, I think the or equal to is a bit of a philosophical choice here. And some people might, because it makes your life easier if you choose equal, because then you're going to need a closed interval domain and you get to use your candidate test and life is good. I think it's a little hard to defend because if you choose x to equal 10, you're going to say that this has a dimension of 0. And some people would argue that's not much of a box. So, but I mean, it's, I think, on the verge of being, you could get away with it. So what would this be then?
Well, x is less than 12.5.
Good. So now we have these 3 inequalities. If we put them all together, we need the most restrictive one that we can, so that it satisfies all of them. That's going to be from 0 to 10. So there's our domain. Okay. Well, should we multiply this thing out? See, 25 times 2 is 50, so 25 times 20 is 500 times that x is going to be 500x. It got really lonely in here for a moment. 25 times negative 2x is going to be a negative 50x. Negative 2x times 20 is going to be a negative 40x. So negative 50x and a negative 40x makes negative 90x squared. That make sense? Negative 2x times negative 2x is 4x squared times x makes that a plus 4x cubed. So there's our volume formula. So we'll take the derivative. So b prime, I'm going to move this out of here. So b prime is going to be and this is where I think you go to your calculator. Because we have restricted our domain, when you graph this on your calculator, now this is some big huge parabola, right? So it could have it's going to have 2 places where it crosses the x-axis. But I think if we only look for the x min 0, x max 10, I think you'll get only 1 in there. It might be worth noting, does it cross by coming from above down or below up? Does that make sense?
My calculation doesn't have batteries.
You're lucky, I've got some loaners available.
Oh, So do we have to say both zeros and then say this one isn't within the range, or can we just?
I think if you already restricted your domain,
Then you can.
then I think you're okay with just saying what that is.
Let's see, the 3.681.
3.681.
Yeah, my boy, we got to plug all that in.
So yeah, you have two choices now, right? So you can do the limit as x approaches 0, limit as x approaches 10, or you can do your number line and argue that it's the only critical point on the domain.
Did you guys get 3.681?
Yeah. Gotta write it down. Oh, yeah. That's why it's so short. Yes, I believe so.
Okay, so kind of two different ways of justifying that. The limits actually are pretty simple on this one because if you look when it's factored, if you plug in 0, that's going to be 0. If you plug in 10, that's going to be 0.
Should one of those limits be 10?
Oh, yes, yes, yes. There we go.
Just let me.
Okay, so either of those is okay. Those are tricky. Okay, I don't know, 4 minutes. Let's see if we can just get an equation for this. Okay, we look for the area, the rectangle of largest area inscribed in one arch of the sine curve. Get that?
I lost points already.
The rectangle of largest area inscribed between one arch of y equals sine x and the x-axis. Setup is the hard part here.
Yeah, I can't remember the x, but wouldn't it be like 5?
So I think it helps to kind of focus your attention on one of these two, but I think this is an easier point. So if we look at the coordinates of that point, because there's a shared point with our rectangle that we're trying to maximize with the sine curve, which is our boundary. So that point has x coordinate x and y coordinate sine x. So now it also kind of holds the key to how we're going to get the length and width in terms of x. So now this length right here, if this is x, by the symmetry of the sine curve, this is also that same x. So whatever that length is, that's the same. So that makes this length right here pi minus 2x. That's the hardest part, I think, right there. And then the height, or the width, is going to be, it's the y coordinate of that point, which is going to be sine x.
So on the test, when we have these, do we have to write y is pi minus 2x, or can you just jump to x?
You can, as long as you can come up with it.
Okay.
So what I'm looking for is, can you get this correct area function? Okay. And then from there, it's going to be calculator active, because, I mean, it's not going to be a nice value, a nice choice. So you'd have to probably either distribute that and then take your derivative, or do the product rule on that derivative, set that equal to 0. Now, the domain is an interesting part here, because if you're really clever, you can really make your life easier. So I think at a glance, you could say, well, the domain has to be between 0 and pi, certainly. Now, if you really think about it, for pi minus 2x,
Yeah, pi over 2.
you can't really let x be more than pi over 2. And so if you say, oh, I can do better than that, that makes your search for the critical points a little narrower. So, very good.